This is the last section of this bending moment equation, and in this section we'll derive that sigma upon y is equal to m upon I, right? This particular section will derive in this equation. Now strategy will follow the same strategy that we followed in case of derivation of torsion equation. In the torsion equation we followed one strategy, that in that case also we find out what was the internal moment of resistance, and that moment of resistance was responsible for taking that bar to its original shape, right? So in case of torsion it was like torque was applied like this, and we found out the internal moment of resistance, and then we compared that internal moment of resistance with the with my value that I found out. The same strategy will follow in this. In this also we'll first find out what is the value of internal moment of resistance. Internal moment of resistance because of the compressive stress and tensile stress produced. We'll first calculate the internal moment of resistance, and then we'll compare that internal moment of resistance with the applied moment, and what is applied moment is m, and that internal moment of resistance is that only. So we'll compare those two things, and then we'll get my desired output, right? Now before I go to that formula, the theory of simple bending once again is very important, and we should undergo that. In this case there is one layer that is called as neutral layer or neutral surface. So for that I drawn one different diagram. In this, if you see in this is the let us say rectangular bar, and in this rectangular bar this is the one middle layer, right? And this is that middle layer which will not experience any type of force when bending moment is applied to it. That means if I apply bending moment to this, like this, then this is the layer on which no force comes upon it, right? Now this layer is called as neutral layer, or this entire surface is called as neutral surface. As of now I do not know what is the location of this neutral surface, right? But that layer is called as neutral layer or neutral surface. And if I cut this section, if I see the side view, or if I cut the section, then what I'll get is I'll get this type of rectangular cross section, and this rectangular cross section, the impression of that neutral layer, is called as neutral axis. And in my, like in your case in the earlier derivation, this is that impression only, and this is called as neutral axis. That is why it is represented by NA. And the same whatever I told you in my earlier case, the same is written over here. If you study this, it will be very easy for you, right? The same concept of theory of simple bending. Now let us first understand, let us first try to solve the our bending moment equation, right? The derivation part. Now in this, what we decided is, we decided to take one very small section of it, and that small section, let us say area of that section is dA only, and that small section is at a distance of y from the neutral axis, right? Now the bending force, the bending stress experienced at this section is, let us say, sigma b. Then the force on this elementary area is bending stress multiplied by area, and that bending stress is sigma b, and that area is dA, right? Okay, so and sigma b, now sigma b is a variable, right? Because sigma b, you know, it will depend upon y. So I can change that sigma b by, I already done this derivation, that sigma b upon y is equal to E by R. So from that derivation I change that sigma b is equal to E by R into y, and that sigma b is equal to E by R into y. I had already done that, and that in that case I transferred this value of sigma b E by R into y into this equation, and that's how the force is equal to E by R into y into dA, right? And if I calculate the total moment of resistance on this elementary area, what will be that? That will be dm multiplied by force into perpendicular distance. And what is that perpendicular distance? Y only. So internal moment of resistance is df multiplied by y, and that is dm, and dm is equal to E by R into y into dA into y, right? Now total moment of resistance means we have to integrate this. If we integrate, then E by R is a constant, it can be taken out, integral y square dA. And you already know, for any shape, integral of y square dA is called as its moment of inertia about its neutral axis. And what do you mean by neutral axis? What is the location of this neutral axis? That still is a question. I do not know, right? I have to answer that. Okay, we'll do that. And but I know it will be about neutral axis, right? Okay, so m is equal to E by R into I, and m upon I is equal to E by R. So this is what the bending moment equation, which is m upon I is equal to E by R is equal to sigma b upon y. And in this case we had compared this bending is moment of resistance by the external moment which is applied upon it. So external moment m is equal to E by R into I, or m upon I is equal to E by R or sigma b upon y. Now in this case we can put sigma b upon y, or we can write down sigma upon y. Wherever value of sigma will take the same value of y. If we take sigma c, then we'll take yc. If we take sigma t, then we'll take yt, right? Okay, now okay, so in this equation, bending moment equation, m upon I is equal to E by R is equal to sigma upon y. The problem was that we already said that in this case the position of neutral axis was not defined, right? We know that this is neutral axis, but where this neutral axis is, that is still, it's a question for us. So the answer of this question is, if we calculate the net force across that neutral axis, then that net force dF is equal to E by R y dA, right? This was the same formula whatever we discussed in that document. So net force is F is equal to E by R integral y dA. Now if we compare, if we try to find out, then we can see that net force across any cross section has to be equal to 0, because on one side it is of compressive in nature, on the other side it is of tensile in nature, and if we add these two it will come 0. Now the question will be in your mind that how can you say it will come 0? If you calculate for any structure, because sigma is directly proportional to y, and it will automatically come as 0. If we calculate this for any definite structure, then we can get that value that it will come 0. That is why if it will come 0, then in that case F is equal to 0 about that neutral axis. Now when F is equal to 0 and F is equal to E by R multiplied by integral y dA. Now E by R cannot be equal to 0, because it is some value. That means integral of y dA should be equal to 0. If integral of y dA is equal to 0, that means that y is measured or taken from the centroidal axis of the cross section. Then what do you mean by this? This means that neutral axis lies upon the centroidal axis. So that means the location of neutral axis is nothing but the centroidal axis of that particular cross section. Right? Thank you.